Types of muscle tissue. So there's the functions of the cardiac system, which includes the major functions which help us to live everyday life. This is such as transporting nutrients, gases and waste products around the body. It has to deliver and remove things such as oxygen and carbon dioxide to allow our muscles to function. It protects the body from infections, and it stops blood loss by clotting using the platelets. And the main function, one of the main functions is to maintain fluid balance within the body and regulate body temperature. This is the circuit which shows the route of blood in the two circuits, the pulmonary circuit and the systemic circuit. The pulmonary takes it to the lungs and the systemic takes it to all the muscles. So it goes from the lungs to the pulmonary vein, which, as you can see, takes blood back to the heart, into the left atrium, and then it goes through the bicuspid valve, which is split into two, which opens when the pressure builds up and the blood falls through, and it goes into the left ventricle, where it then goes through the aortic valve up here, through to the aorta, and follows round through. This is where it then reaches the muscles that is needed, and diffusion and gaseous exchange happens due to the capillaries, and the capillaries being so one cell thick, it allows diffusion to happen quickly. Then through the systemic vein back towards the heart, through the vena cava to the right atrium, and then to the tricuspid valve, which is, instead of the bicuspid, is in 3, and then into the right ventricle to the pulmonary artery, where it goes to the lungs, and then this happens again. So as you can see, the pulmonary circuit, which is at the top, as I said before, is from lungs to heart, and that's just that circuit that continues, whereas the systemic is from the heart to the muscles and all the way round. The way you can see the difference between the red and the blue is where the red is oxygenated blood. So the muscles need the oxygen, so it goes towards the muscles and then back up to the heart, where it goes to the lungs to be re-oxygenated. So here's more of the heart structure. So some of the main parts that we've already gone across. So the muscle walls here of the left ventricle here are needed to pump blood all around the body. This is the side that goes to the muscles. And obviously the muscles are further away than the heart, so this side is thinner as it doesn't need to contract as much. So there's less need for muscle wall. And up here you can see even less of the muscle wall, as that is literally just contracting to get it down into the ventricles. The conduction system. So the electrical system of the heart creates an impulse from the SA node, which is then passed along through the atrium, which helps it to contract, and with the going through the valve that we spoke about, which then allows for the blood to flow through, and the impulse that is sent from the SA node goes to the AV node and down the bundle of his to the bundle branches and Purkinje fibres, which helps this to contract the bottom of the ventricle, which helps to push the blood up because it's contracting from the bottom to the top. So it goes from the SA node, or the sinoatrial, and then the atrial ventricular, to the bundle of his, bundle branches, Purkinje fibres. Compared to that, we've got the cardiac cycle, which is how the heart contracts and how it feels. So diastole happens, which is the relaxation phase where it fills, and systole happens in the atrial and ventricle, which is where it contracts and the blood is removed. So the upper chambers are the atrium and the bottom of the ventricle. Atrium and ventricles contract and relax in the conduction cycle, moving blood around the heart and therefore around the body. So the conduction system controls the cardiac cycle. This is done by atrial diastole, where the atrials fill, and pressure builds up and when the pressure builds up so much, about 70% of the blood falls through the valve that gets open due to the fact of the pressure on the valve. So the blood falls through, however, it can't all go through, so 30% around is left. So the atrials contract actively, so they contract pushing through the blood, so it contracts from the top to the bottom, where the ventricles then become full and the SA node sends an impulse to allow ventricular systole. So this is where the blood is moved, so the ventricles contract from the bottom because of the Purkinje fibres all the way up to the top to remove all the blood. So this process happens from atrial diastole to ventricular diastole, which is passive, so that's the 70%, atrial systole and ventricular diastole, which is active, which is the rest of the 30%, and then ventricular systole. And this process happens again. So timings for this. So ventricular diastole happens in about 0.5 seconds, and the systole happens in about 0.3. That's why our total heartbeat is 0.8 seconds, which is this whole process. So autonomic influence also affects how our body works. So when exercising, the lungs need more blood and oxygen to allow them to function. It can be done in many ways: hormones, the autonomic nervous system, and part of the autonomic nervous system is the parasympathetic nervous system and the sympathetic nervous system. So the parasympathetic inhibits heart rate. So parasympathetic is carried through the vagus nerve, where a chemical ACH is released, goes across the synapse to the SA node, where it knows to slow down the heart rate and just tells the body that it doesn't need as much oxygen and blood that's being done, compared to the NS node, which is a sympathetic nervous system, which increases heart rate due to the release of norepinephrine, which is a neurotransmitter, which then obviously does the same, travels across the synapse to the SA node. This is the accelerator node due to the fact that it increases, as well as the autonomic nervous system being in charge of getting blood to the muscles and oxygen. It can also be affected by hormones, so adrenaline can increase the heart rate due to the fact that your adrenal glands send a message saying we need more oxygen, and it happens like that as well. So blood. Blood has a structure which, when put in a machine and spun round for ages, separates. So it's done with around 55% plasma, which is shown in yellow, and of which of that it's 90% water, 8% protein and 2% hormones such as insulin. So this is the majority of the blood. As you can see in the middle, just in the white, it's less than 1%, which is white blood cells and platelets. And the platelets, as we said earlier, are used for clotting, which helps stop blood loss. And then at the bottom here we've got the 45% that's left over for red blood cells. And these red blood cells carry oxygen and remove the CO2 from the muscles. So this is what you'd expect to find in someone having an equally split. However, some people have anemia, which is a low proportion of red blood cells. So this is why they have a much smaller and they've got more plasma. And then you've got this one here, which is an elevated polycythemia, which is a high proportion of red blood cells, so the opposite of anemia, which does mean that there's less of the plasma, which carries the protein and the water and hormones. So this does affect how people live. So here you've got the function of each of them. So as we said, white blood cells have antibodies which help fight infections. So someone here may struggle more to fight infections than someone with anemia, but better still, normal blood, which is equal. So the blood vessel structure. So this is a large vein, and then we've got different size veins, and then go to venules, and then the same with the arteries on the side with arterioles and capillaries. So the capillaries are one cell thick and have an endothelium cell, which is the only cell which covers the capillary, which is also included in the majority of the other vessels. So they are lined with the tunica intima, which in most cases is the endothelium cell. Tunica media, which has elastic fibres, so on the arterioles it has smooth muscle tissue on the outside, which allows the muscles to contract, allowing ventricle, systole and diastole. As well as this, there's the external layer, which is connective tissue, which allows it to connect to other arteries and things like that. However, not all of them have, as you can see with the arteriole, that's the only layer it has is the smooth muscle cell. So as I said here, resistance can be increased when vasoconstriction, vasodilation happens, due to the fact that if they become more narrow, it's harder for the blood to go through, so the resistance increases. So with the precapillary sphincters, these are located at the top here. So this is where the arterioles come into, and this is what I was saying about the smooth muscle. They allow them to contract and dilate. So here we've got precapillary sphincter, which also can contract. So here, this is a contracted state where it becomes a lot closer together. This stops the blood falling through there, so it can be diverted to somewhere where the blood is needed. So the blood will flow through the capillary bed until it gets to a point where it can pass. And then if they are needed, the sphincters relax and dilation happens where the blood can then go through. So as well as this, we've got pocket valves, which, as you can see here, if the blood was falling down, it would fall into these what look like pockets. These stop blood from going back, so these are located in the veins. So blood would be coming up, and with gravity especially, it can occasionally fall down, which obviously we don't want blood to be stuck in the middle of our veins because it needs to go back to our heart, so it can be used in the pocket valves. So also the lumen, which is the middle of the vein or the artery, which you could probably see in the other diagram. So this is showing the artery, how the lumen is very circular but not too big. In the vein, however, it's much larger, however not an equal shape. And obviously in the capillary, where it's only one layer, the lumen's a lot different shape, but as you can see, it's still quite a large area. So here you can see the lumen here, which is a much more rounded, smooth shape compared to the artery, which is slightly smaller, and also a different shape, which doesn't allow blood to flow as easily due to the fact it's often going down, so it has the use of gravity compared to the vein, which needs to be smooth and easier surface to run against due to the fact the veins have got to go against gravity. And I think that's everything.